So concurrency and control over time. So this we have already discussed. And more specialized processors, memory architectures, IO mechanism, operating system, and sensors and actuators. So this also we need to select. Then fixed point and floating point arithmetic. Hope I have already handled this on fixed and floating point arithmetic. So then our architecture should also have pipelining and caching. So caching, anyway, I'll just come to that in the other next topic. Interrupt driven or multi-threaded software. So interrupt driven means, for example, if any IO device needs a CPU, so IO device it needs a CPU. So then the method is the IO device will place a request as an interrupt request. So once the CPU is free, the IO will be allocated. The service of the CPU will be allocated to the IO devices. So this is what generally interrupt driven. In case if you have multi-threaded software there, so the each IO devices will be handled by a multiple thread like this. So thread 1, thread 2, thread 3 like that, it will be handled there. So either we need to have the interrupt driven system or multi-threaded software. Then synchronization. So we have synchronization in terms of shared memory synchronization and timing synchronization. So as you all see that in your desktop computer, you will be having a timer inside your laptop. The motherboard has a timer. So that timer will be integrated with the timer in your operating system. So your OS will have a timing. So this timer, always the hardware timer have higher priority. So in case if the timer is not counting its time, so then the operating system also will be altering its time according to the hardware timer. So we have synchronization between the hardware timer and the software timer. So hardware timer, the generations, there are multiple hardware timers. So one thing is called as a circuitry called as 555 timer. There is a circuitry. Then quartz. As you know that in digital watches, you have this quartz as a crystal. It's a crystal oscillator. So that will oscillate based on the oscillations. The timing signals will be generated, and you'll get the quartz. So that is one. Software timer, we can write a simple logic in C programming or C++ or whatever logic. We write a software timer. So usually there will be only one hardware available on any microcontroller or microprocessor, and that will be synced with the software timers. So that's how the computing happens in the case of design. So the choice of designing is very. I mean, it should be met at any cost, because if the design there is a flaw in the design, it will be reflecting on the entire cost of the project. So that is how the design has to be very good enough. So if the design is so weaker, then the product might be a collapse. So if it is a software, you can correct it by replacing the code. But if it is a hardware, then it will be a failure. So one good example, you see there are many hardware products have been failed over these years, mainly because of the design aspect. So design uh, should be good enough. Next thing is the analysis. A design without specifications cannot be right or wrong. It can only be surprising. So this is analysis. So analysis means after the specification is been arrived at, we have to think of the how we can able to underlay, how we can able to design the system. So that's what this analysis. Every system must be designed to meet certain requirements. So you are designing the system to certain requirement. So generally, IEEE they has a requirement specification document called as IEEE document. So we generally called as IEEE SRS. SRS means software requirement specification. That's what the SRS means. So IEEE have a standard of software requirement specification document. So in present engineering practice, it is common to have system requirements stated in natural language such as English. So generally, the software requirement specification will be specified by the basic English language only. So basic statements that is written in English, and it will be given as a SRS document. So many generally the clients will sit with the companies, and the client will be narrating the requirement specification. So there are some specification guidelines how to specify it. It is important to precisely state requirements to avoid ambiguities inherent in natural languages. So ambiguities are always common in many of our systems. So one example is we have something called as a real-time clock. So generally, RTC we generally call real-time clock. So real-time clock means the timer signals works with the deadlines. So this real-time clock. or the real-time clock will usually triggered with the help of an interrupt mainly. So whenever there is a high priority interrupt, the real-time clock get triggered and then some actions will be happening. So this real-time clock can be implemented. The alternative is the timer, any timer. Suppose I want a real-time clock to be deployed, but instead of that, because of the complexity of the circuitry, someone design a hardware timer here. But the hardware timer cannot work with the deadline. So in that case, so there are these are the ambiguities that we can experience in many of the design flaw. Okay, so these ambiguities are very inherent and particularly in natural languages. Okay, so since we are using only English as one of the language, so many people, those who don't understand English, so they may be in problem of these ambiguities. So that cannot be avoided. But CPS is heterogeneous system. They are harder to model, harder to design, and harder to analyze than a homogeneous system. So generally, homogeneous systems are very easy to handle, but whereas heterogeneous systems are very tougher to handle. Heterogeneous system means the system is made of many different components which are manufactured by different vendors. So that's what we call heterogeneous. Homogeneous system means the system know itself how we can able to perform with other fellow counterparts. So that's what homogeneous system. Okay. So one good example for heterogeneous system is if you take a laptop, the laptop processor comes from Intel or AMD. The laptop GPU comes from AMD or NVIDIA. Yeah. So that is the GPU card comes, graphic cards. Then the memory comes from Taiwan with some company, and the hard disk come from somebody else, and the motherboard comes from Intel original motherboard or Gigabyte motherboard or Asus motherboard. So there are many multiple motherboards versions are there. So in the motherboards, if you see the timer is from different piece of frequency, and there are multiple things, and the screen is from different peoples, and the Wi-Fi is from different. The Wi-Fi circuitry is from different. Bluetooth circuitry is from different vendor. All things together assembled and converted as a single laptop. So
So MacBook is homogeneous. Is MacBook homogeneous?
pardon?
Is MacBook homogeneous?
Yes, yes. So that's what I'm just coming. Anyway, we cannot say purely homogeneous, but usually they have their own product. So that means the software and the hardware, they come together as part of a particular package. So that means they write the software for their own hardware. So they know how their hardware behave. So for that they write their own software, and both in work in tandem, and that's why you will feel that the system is always powerful, and it is and so fast in operation. So it is some kind of homogeneity there, because again screen is from Samsung. So even Apple purchases screening the screens, the displays from Samsung, and the hardware is completely by them all, their own. Again, I will just come to that in the next topic. I'll be coming to that. So careful modeling, design, and analysis have to be performed for a perfect cyber physical system, as it is completely heterogeneous. So in your case, how can you design a heterogeneous system? So that's what this entire this subject is. We are going to deal with that. Okay. So I'll just go to the processors here. So already I have just this for them. Okay. So now I have this embedded processors. So or we can say that processors for cyber physical system. So we can call something like sci-fi sys. Okay. So I usually represent like this then. CPS or sci-fi sys. Okay. So processor design for sci-fi sys. So generally processor design in the sense that so we have two kinds of processors. So we have been seeing over these years. Okay. So as you all started using your system now, maybe even I have my 15-year-old son. So he never likes laptop. So he never liked laptop. He always tried to have a mobile phone or a tablet with him. So all the classes he will attend, everything he will do, even present a PowerPoint presentation, he use this tablet only. So though I am advising him to use a laptop, he never take it as granted. So he always use a tablet for designing his own PowerPoint for school presentation. But I just think that, okay, am I the only one who is in 70s kid, and then I am just using my laptop? Why this current generation? So maybe I see some of our students, they usually have a laptop. So when the day one, when parents started calling us now for first years, sir, which laptop I can go for, whether I can go for a high end or a low end or a medium end or something like that. They keep on calling either one of our faculty members on which laptop they want to procure. So now, having said that, we are coming into processing. Okay, but uh, but the knowledge behind this processing, so many people they didn't understand about it. So this session I will be explaining you the fundamentals of these processors. Okay, so why really we need processor, and how the processor thing have been evolved over these years. Then what difference between a processor and a controller. So when do we need a processor, when do we need a controller? Okay, so understand these basics clearly, so that you will never forget for your life, and you can keep it as counter that you have learned life skill today. Okay, so there are two things. One thing is the general purpose processor, so we call it as general purpose. The second thing is embedded processors. So it may be embedded system or the processor which is embedded in the hardware. So anything you can say. So general purpose processor and embedded processor. So generally embedded processor we can call it as a controller as well. So we can call it as a controller as well. So there are two aspects of it: controller or embedded processor. Now, generally when dealing with this computing, there are two persons. Okay, so one is von Neumann. Sorry, so von Neumann versus Harvard architecture. So there are two guys. Von Neumann is a scientist. He was working in university called as Princeton University. So either it can be Princeton architecture versus Harvard architecture. Okay. So initial days when von Neumann, he was a scientist, he was and the personal computing was evolved during the 70s. It was slightly evolving. So that time he suggested one concept called as program memory and data memory. So program memory and data memory. So he suggested a concept. Okay. So program memory and data memory. So what do you mean by program memory? So one example here is when I say move a comma 32h. If I say something hash 32, move a comma 32h. So this is called as a mnemonic. So mnemonic. So in microprocessor, you might have studied about this instruction set. When you convert this into an opcode, let's say when you convert this into an opcode, you call this as 32 is one number, and the equivalent to move a, we have a value called as 45 or something, 45 or 4a, something like that. We'll let you have 4a. It's hexadecimal. To indicate hexadecimal, I use 4a and 32. So 4a and 32, these are all opcode, operation code. Okay, this is hexadecimal number. So among that, 32 is the data. So 32 is the data, and 4a is the program. Program means it is an instruction. So this we call it as an instruction. So this is instruction. This line is an instruction. Okay. Now this is one instruction. This might take how many t states? So you might have studied about t states. So t states mean time states. So how many time states this instruction will take? Move a will take one state, and moving the value 30 to another state. So two t states. Sometimes registers will take three t states. Sometimes only one. Let's say for example XRAA. What is XRAA? So X are the content of A with its own thing. So that means you are clearing the accumulator. So one method is CLR A, that is clear the accumulator. Then XRAA, or else you can use move immediate A comma 00H. That means these three instructions makes the accumulator to clear. Okay. So this takes two T states. This take only one, this take only one. So if you want to avoid the timing, so you can avoid this instruction. So don't use MVI. That means it takes more T states. So this way they optimize the time occupation. Okay. Now I'll just come to that. So this is instruction. So now that time von Neumann have suggested that let the program memory will be separate, and the program memory and the data memory will be together. Okay. So what he did is program memory and data memory in same logical space. In same logical space. That's what von Neumann suggested. So this is von Neumann architecture. Okay, he suggested program memory, data memory in same logical space. So logical space means a memory space. Okay, he wanted to have in the same space. So now in our case, what happens? 4A and 32 will be in the same logical memory space available to processors. Okay. Now to fetch these values, so instruction processing means what we call MIPS. MIPS is billions of instructions per second. So your processor will be operating upon how many instructions per second. It depends. So for that we call it as instruction cycle. We call instruction cycle. So what is the instruction cycle of each and every processor? We have a separate calculation for that. Okay. Now how many millions of instructions per second the processor can handle? So that many seconds. So in that case, what it will do is we have to apply clock to fetch. So clock 1 and clock 2. So we need 2 clocks to access program memory and data memory for a single instruction. So one instruction, but 2 types of memory is used: program memory and data memory. So you need 1 clock cycle, 1 clock signal for data memory. You need 1 clock signal for program memory. Okay. Now, as per our formula, power is directly proportional to frequency square. Frequency square. Power is directly proportional to frequency square. That means the occupation of power will be, if your frequency is high, your power also will be high. So that's why in generally in desktop computing, if you are a gamer, you might be knowing about overclocking. If you play games or if you are developing games, you might be knowing about overclocking and underclocking. So overclock and underclocking. So overclocking means beyond the capacity of the processor, you are increasing the clock frequency for the processor to make it faster. That is overclocking. Underclocking means you are just doing it underclocking. That means less than the stipulated range. So there are two things. Overclocking, so sometimes you need more power for your gaming. So in that case, you are doing overclocking. In the time, what happens is your battery will be going down very fast. The reason being, the frequency increased, automatically the power is directly proportional to frequency square. So that means the frequency increases, the power also will be drastically increased. In that case, your energy in the battery will be drastically reduced. So that is a formula there. So P is directly proportional to frequency square. So because of this clock 1 and clock 2 in the program and data memory separate, so we need 2 clocks for fetching one instruction. So then when Harvard architecture, they suggested that why can't both be in the same different logical space? Let program memory in the different logical space and separate data memory in the separate logical space. Data memory. So both in the separate. So what he has suggested is give 1 clock signal program memory to fetch it, and another same clock signal to fetch the data memory. So he applied only 1 clock signal to fetch the program, to fetch the data. Just only one parallel clock signal. Okay, that's what. But after that, in same Harvard, they designed another thing called as modified Harvard architecture. Modified Harvard architecture. What they suggested is program memory plus data memory and prefetching. Prefetching. So prefetching means what? Fetching the next instruction. So fetching the next instruction. So that means some initial context of the next instruction also you will be fetching it by the previous instruction. So that's what they did with 1 clock. Just only 1 clock that can fetch the program memory, that can fetch the data memory, and they can fetch the next instruction which is going to happen. So it will be in line because it is in series. I mean, synchronous serial programming. So one by one, the sequential programming, one by one it will be running. So the next instruction will be coming. So that instruction will be taken out there. Okay. So that is called as prefetching. Okay. So that is modified Harvard architecture. So Princeton, Harvard, modified Harvard. But there were some problems in modified Harvard and Harvard for desktop computing. So desktop processor, those vendors, what they have suggested is they wanted to retain with von Neumann architecture or Princeton architecture. So still this day, all the desktops they use the architecture of von Neumann architecture, Princeton. So the program memory and the data memory are in the same logical space. You use clock for that. But the main thing there is they are generally processors. So processor. Okay. So Intel, if you say Intel I series, i3, i5, i7, i9 like that. Then we have AMD. So AMD also now comes with the Ryzen. So Ryzen 3, Ryzen 5, Ryzen 7, Ryzen 9, like that, they also bring it. So most of them uses the one Neumann architecture still this day because it's a processor. But Harvard was adopted by embedded systems, or is the so-called we call cyber physical systems. So Harvard completely adopted with by the because we need miniature devices that needs less power. Again, we need lower clock frequencies. So lower clock. So they wanted to have. So that's why still this day, let's say if you take Intel 8051. Have you studied Intel 8051 so far? Students, have you studied Intel 8051?
No, sir.
Was a 8255.
It's
8255 is a PPI, Programmable Peripheral Interface. Programmable Peripheral Interface. So this is 8255. So you might have studied with the 8086, right?
Yes, sir.
yes, sir.
Yes, sir.
So
Only 8086.
yes, okay. So 8086 you have studied. So it's a microprocessor. Okay, but here Intel 8051 is a microcontroller. Okay, now what makes the difference here? Okay, so 8086 again it's an x86 processor. Okay, so 8086 is a x86 processor. That means first we have 86, then 186, then 286, then 386, then 486, then 586, then 686. I don't know how 86 there or not. So generally we call it as x86. Okay. Now generally this x86 is a 32-bit architecture. 32-bit generally. After that, after a period of time, they converted into x86_64 called as 64-bit instruction set. 64-bit instruction set. So that's how the way the processor have been evolved. But Intel 8051, what it has is it's a microcontroller. So microcontroller. So that means a processor plus IO ports plus memory plus interrupt controllers plus timers or counters plus flash memory or plus watchdog timers. Generally, we call WDT, watchdog timer, etc. plus etc. So this is called as a controller or a microcontroller. So addition of everything together and it's called as a controller. Okay, but Intel 8086, so Intel processor still now i5, i7, i9, it is called as a processor, not a controller, because the processor comes separately, the interrupt controller comes separately, the IO ports come separately, so everything is separate in a motherboard. But whereas in embedded systems, everything comes on board. Now everything comes on an IC, so that's why they call something called as SoC. So that is system on chip. That's all they call SoC, system on chip. So that means everything on a single IC, you get everything. So that's what they call. So generally, Apple processors now, whatever they, let's say the M1 processor, what they launch, what Apple launched is it's a system on chip, SoC. That means your GPU is there, your CPU is there, so everything is just there on a chip. Okay, so that's how the processing thing have been evolved, von Neumann and the Harvard architecture. So embedded systems they follow Harvard, whereas desktop system they follow von Neumann. Now when I come to this 8051, Intel 8051, it is an open architecture. So open architecture means the source code is free. So 8051 is an architecture, the source code is free. Okay, and it's something like the IC will be looking like this. So the IC will be looking like this. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. This side also 20. Okay, so this is what the pin contains. So one, this will be VCC, this will be ground. All other pins have totally 40 pins. Among these 40 pins, 32 pins are ports. Pins are IO ports. So IO ports means somebody told 8255. So 8255 will have ports, right? Programmable peripheral port. That's what PPI. So similar to 8255, we have here P0, P1, P2, and P3. So totally 8 into 4, 32 pins. Okay. Then remaining 6 pins are there. Okay, timer, counter, something like that. So the pins are overloaded. That means overloaded means the same pin have two different purposes. Okay, that's how the IC configuration. Now this architecture is open architecture. Intel have given open. So open source means let's say a company wanted to, let's say you take example Philips, Atmel. There's a company Atmel, then Atmega. So these companies they also wanted to have their own 8051 microcontrollers. What do? Is they can download the open architecture, they can fuse it to their IC integrated circuit, and they can manufacture their own IC. So that's what these companies are doing. So they have 89C52, 89C51 example. So these are all some of the the market is available microcontroller with 8051. They have additional functions. In some control, general 8051 have 2 timers, but these guys have made 3 timers. So it doesn't have a watchdog timer. They have a watchdog timer. It doesn't have a flash memory inbuilt. They have a flash memory. Don't need kilobytes. Here it is 256 kilobytes. Like that, you can upgrade everything as per your need. So that's what Intel have done it. So it is open architecture free. So in case if you are from electronics background, if you want to try out your own IC, you can download the architecture. So the 8051 is still open under VHDL and Verilog. So it is freely available. You can download it, you can use it. Okay. So that is on Intel. But you guys have heard about something called as ARM. ARM is called as Advanced Risk Machines. Advanced Risk Machines, ARM, that is ARM. So this RISC is called as Reduced Instruction Set Computers. That's what RISC. Please don't forget all these values. Okay, so all these things are should be known to you. So RISC, we have something called as CISC also. Complex Instruction Set Computers. Okay, so CISC 8051 is CISC. 8051 is CISC. Complex instruction set means the number of instructions are very high. That means high means more than 100, 75 to 80 instructions. So let's say move A comma B, then move B comma C, then move R1 comma A, R2 comma A, R3 comma A, something like that. A comma R3, A comma R1. So like that, there are multiple instructions. So you have a complex set of instruction set that you need to remember. So that's why this ARM came. So ARM, what they did is reduced instruction set, ARM. Reduced instruction set means it will have something move A comma B comma C, something like that. So totally 30 instructions only. So only 30 instructions, reduced instruction set compute. Okay, that's how ARM brought it. So ARM is an IP core. So generally ARM is an IP core. IP core. IP core means intellectual property core. Intellectual property core. So what does it mean? So intellectual property. Have you heard about something called as patents? So what is a patent will do? Let's say you see that there's a small 3 circles, no? So whenever you feel bored, if you are stressed, you will be doing that. What is the name of the thing? You have a I forgot. Say sometime 3 years ago, it was so popular. So there will be 3 wheels will be rotating. So you can just make it like this and then
Fidget spinner, sir.
Fidget spinner. Fidget spinner.
Fidget spinner. Correct. Fidget spinner. It's right. So fidget spinner was a patented work. Okay. So initially they got a patent, but any patent across the globe, it is only for 20 years. It's only for 20 years. After 20 years, the inventor they no longer they can earn the royalty or whatever. So you cannot pay them the cost. So it becomes open after 20 years. So any country, I mean, whether it's Australian patent or American patent or Indian patent, it's 20 years only. So up to 20 years, you can make business from your from the device what you have. Okay. Similarly, ARM is an IP core. What ARM will do is they give the architecture to the companies. Okay, you take my architecture. I have a basic circuitry that provides the ARM. Okay, so they give the architecture. Anybody download the architecture, they use the architecture, they produce their own devices. So it's a hardware description language will be given to them. So those languages they put in their own ICs, their chip, and they add all the functionality like how do they do in Intel 8051, and they invest in their products and they sell it. But ARM says that for each device pay me a royalty. For each device pay me a royalty. So you can say Snapdragon is ARM, this on ARM. So Apple A series, all the A series processor, M series processor, now M1, that is also from ARM. So for each device, see, please remember, MacBook, Apple Mac is there with Core i5. I have a MacBook Pro in my home, so 16 GB RAM, Core i5 10th generation. It's a processor, 512 GB SSD. I have this device. Okay, now I have been feeling that this is good. This is a very good processor. But recently, a month back, I got a M1 chip. Okay, I got a M1 chip. See, I'm a general architecture person, so I would like to play around various architectures. So even I have some boards also. See, I have some hardware boards also. It's sent by IIT Madras for NPTEL course. So this is a small board. I have Arduino. I have Raspberry Pi. So I want to try out all the hardware devices. Some are in the laboratory. So I'm fond of these processors. I want to see their benchmarks like that. So that's why I got a M1 chip also. M1 processor. I got a Mac Mini because I want to do multiple stuff on a Mac Mini. But I just wonder that this MacBook Pro was there for past 2 years. I'm holding that, but the Mac Mini just arrived with 8 GB RAM and 250 GB SSD. It almost 5 times powerful than my MacBook Pro, which having 16 GB RAM. Because Core i5 10th generation is given by Intel as a chip. You cannot do anything inside the chip. So the chip has to be placed in the motherboard, and all the motherboard fixing has to be done by Apple or any company in that case. But ARM is not like that. They give the description language to you, so that you use it in your own IC. You just manufacture the IC, you just do all the stuff and fix it on your own thing. So that's what ARM is doing. So that's why ARM has taken over the market. But please remember, the next 5 years to 10 years, there will be a paradigm shift in the complete computing paradigm of everything. So in all the aspects, ARM will enter into it. So far it never in the desktop market or the laptop segment. Now they are already into it. Now all the even Microsoft designed their
Sir,
operating system for.
even nowadays, HP laptop is releasing Qualcomm
Yes,
Snapdragons.
yes. So that's what you can see in the next 5 years. You just see everything will change to ARM. Everyone will be moving towards ARM. So Intel has to have to do something else to grab the market. So that's what is happening now because it's really very powerful. So if you have not experienced, maybe next time when I'm in the home, if I take the class, I'll just show you the Geek Bench. There is a software called as Geek Bench to identify the performance of any processing system. So it's really very powerful. So that's what this ARM is doing. But we can internally learn about what is there inside ARM. Maybe I'll just give a slide maybe in the next class. So how that ARM controller architecture looks like and how powerful it is, so that I can able to show you in the next class. So why I am telling you is that we have two sections of it. One is embedded system, another is the desktop system. So in the embedded system, we call it is the CPS system, and this is a desktop system. So in the desktop, it goes for one human architecture. The embedded, we go for a hardware architecture. So the data memory and the program memory in two different logical space, but still we use the same clock frequency to access the thing. So that's how the way we want to make the system steadily faster. So that's why in many real world application, like so arm of a robot. So if you want to design arm of a robot, if you want to send a space shuttle, if you want to send a planet, if you want to send a satellite to the planet, to Mars, or to if you are sending some Chandrayaan 2 or Chandrayaan 1 to the moon station. So all these things they use embedded processors. They never use any general purpose controllers. They wanted embedded processors. Cyber physical systems also needs an embedded controller, not a desktop computer. Okay. Now, having said that, how can I design? How can I select my application demands? Let's say one example is this. My system demands 10 microsecond delay, less than 10 microsecond delay. So, which processor I can choose? I can choose. Okay. Should not be bulky. The design flaw is should not be bulky. Okay. Should not be bulky. So it is something like that. I want 1 cup of tea. Okay, so let's say see the cup. I want 1 cup of tea, but for that I can easily drink with this like this. But in case for 1 cup of tea, if I take this water bottle for 1 cup, it will be coming up to this. But both will hold good. Okay, but what happened to the space requirement? This occupies huge space, but this occupies this 1 cup of tea. That's why 10 microsecond I can able to use a Core i5. No issues. For 10 microsecond design, I can use Core i5. But it is like for 1 cup of tea, I'm taking this water bottle. Okay, that's what it means. So I don't need that much. So I want so in that case, what I do is I can think of a processor that has 12 megahertz frequency. 12 megahertz. The blind rule is 1 by 12 megahertz. So frequency domain and time domain. So 1 by frequency is equal to the timing. 1 by 12 megahertz. What is the value? Or let's say 10 megahertz we will take. 1 by 10 megahertz. What is the value? 1 by 10 is 0.1. Megahertz will be 10 power 6. If you take 10 power 6 in the numerator, it becomes 10 power minus 6. So 0.1 microseconds. So this is my instruction set timing. So my timing. That means each instruction on my computer will operates at 0.1 microsecond. That means one instruction 0.1 microseconds. That means what happens in 1 second? If it is 1 second, what happens? So that means 0.01 into 10 power minus 6 into 10 power 7. So that means I'll get one instruction. Then how many instructions I can able to execute? So that's what I call 10 MIPS. Sorry, 1 MIPS. 1 MIPS means 1 million instructions per second. So this is simply like that. So if I want to execute, one instruction takes 1 microsecond. That means in 1 second, how many instructions I can execute? Ideally. So that means one will be 10 power minus 6 and 10 power 6. That means almost I execute 1 million instructions per second. So that's what it means. So this is how the way I can select the processor. So I can say that okay, Intel 8051 have 0.1 microsecond or 12 megahertz delay. So let me use Intel 8051. If I want more, 300 megahertz, if I want more, then I can go for an ARM controller. So again, ARM controller have 3 versions. So ARM have 3 series: M series, then A series, then they have R series. So they have again the name itself it says 3 kinds of thing. M series mobility for mobiles, A series for application, R for some research and other kind of processors. They have 3 kinds of series of processors. ARM has. Okay. So Snapdragon Qualcomm also comes under ARM controller. So Qualcomm also is paying some royalty to ARM. So the entire ARM is maintained at ARM.com. Company called as ARM.com. They are maintaining the entire IP core of the ARM controller. Okay. So the entire world now almost 96% of the entire world, I mean, almost the handheld markets. If you take the set-top box, if you take the washing machines, and even if you take the even mobile phones is complete. Okay, mobile phone, tablets, even laptops also now they are protruding, and any household devices like if you have a processor in with the Bluetooth speakers, if there's a processor inside, that also comes with ARM nowadays. Okay, so everywhere ARM comes. Okay, so that's how the way ARM controllers play a vital role in our day-to-day life. But we are having different branding. So even MediaTek was there. That is also coming via this ARM. Okay, so everyone now they just go with ARM controllers. Now this design aspect, how we can go for. Okay, so this is the introduction to this processor. How we can design a processor, or how we can select a processor for a particular application. Maybe we'll see some more applications in the days to come. So just to show you what are the different kinds of processors. Okay. So any queries, students?